Okay, we want to talk about the ideas of divergence and curl. And we've seen examples in the preceding clip of a vector field or a series of vector fields that all diverge. They all point out away from the origin. They don't curl around the origin, they diverge from the origin. So we're going to define divergence and curl, but let's think of those examples as we do so. Now, from your study that involves the gradient, we're used to the del vector, or the del operator. The del operator is the partial with respect to x times I plus partial with respect to y times j plus the partial with respect to z times k. The del operator applied to a scalar function is the gradient, and that's fxi plus fyj plus fzk. Applied to a vector function, we can't multiply a vector by a vector in the sense that we've sort of applied this operator to a scalar. It's almost like a multiplication with distributive laws and so forth. But there is no single operation of multiplication on vectors. In three-dimensional space, however, we do have scalar, dot product and cross product, and the divergence and the curl are going to be simply related to the dot product and cross product. So we're going to say that the divergence of a vector field f of x, y, z is the del operator dotted with f of x, y, z. And also that the curl of f of x, y, z is the del operator cross product with f of x, y, z. Now, what is del dot f of x, y, z? Well, f of x, y, z, remember, is a function mi plus nj plus pk. So we can make sense of that by simply writing out the del operator and the typical representation of f, and that's going to be partial with respect to x, I, plus partial with respect to y, j, plus partial with respect to z, k, dotted with m, I, plus n, j, plus p, k. How do we do a dot product? Well, in a dot product of actual vectors, we'd multiply the I, the j, and the k components paired up in that manner. With a vector operator, we treat it pretty much the way we would with a dot product of two vectors. We do the partial with respect to x of m plus a partial with respect to y of n plus a partial with respect to z of p. And that gives us then, well, let's write it out this way. Partial of m with respect to x plus partial of n with respect to y plus a partial of p with respect to z. Now that's just a scalar valued function. And we could write that as mx plus ny plus pz. An example for the simplest of the functions we've already looked at, if f of x, y, z equals xi plus yj plus zk, then del dot f is partial with respect to xi plus partial with respect to yj plus partial with respect to zk